Hello, my name is Alexander Rincon, and today I will be presenting my final project of Intro to Material Science, and it will focus on the molar absorptivity coefficient of sunscreens. So, in order to understand the scope of the project, it is important to understand the Beer's law, which describes the ability of a material to impede light from passing through it. This is essentially the absorbance of the material, and in this simple equation, you can see that absorbance depends on the concentration of solute in the solution, the path length of light, which is the distance that light needs to travel through the material, and the molar absorptivity coefficient, which is the probability of light transition. In this equation, it is simple to see that as the molar absorptivity coefficient increases, absorbance also increases. Now focusing more on sunscreens. So the four main components of sunscreens are active ingredients, formulation stabilizers, sensory enhancers, and added extras. In this presentation, we're only going to focus on the first component of sunscreens, which are active ingredients. These active ingredients work as a ultraviolet filter that absorbs or reflects UV radiation. This radiation can come in two types, which are UVA and UVB light. So UVB light, as it has a shorter wavelength, interacts with the surface of the skin and causes damages to the DNA in the outer skin layer and sunburns. On the other hand, UVA light, since it has a longer wavelength, can dive deeper into the skin and cause minor damages such as wrinkle or tanning, or even damage to the DNA. As a way to differentiate sunscreens, we can look at their active ingredients and see if they absorb or reflect light. For example, in physical sunscreens, um, this sunscreen cells at the surface of the skin and reflects incoming UV light, which some examples of this component can be zinc oxide or titanium dioxide. On the other hand, chemical sunscreens are the ones that are absorbed by your skin and convert UV rays into heat when they try to penetrate the skin. Some examples of these components can be oxybenzene. So the goal of this experiment is to compare and contrast the molar absorptivity coefficients of these two types of sunscreens. So the materials for the experiment are a UV meter, a glass or plastic cuvettes, a digital scale, graduated pipettes, physical and chemical sunscreens, disposable plastic cups or small containers, a ruler, rubbing alcohol, and water. So the sunscreens used in this experiment are shown on screen, and the physical sunscreen active ingredient was mainly pentabutene, while the chemical sunscreen active ingredient was adobenzeno. Now, focusing on the procedure of this experiment, we will need to first weigh 0.3 grams and 0.5 grams of the physical sunscreen using a digital scale and adding each quantity to a different plastic cup. Later, we will add 10 milliliters of water to each plastic cup. Using these two solutions, we will later make 9 solutions with the following concentrations. Now, this will require to dilute the solutions using the right amount of water to get the right concentration. Later, we will add 2 milliliters of each solution to a different cuvette using a graduated plastic pipette. We will do the same thing, but now adding 2 milliliters of water to a cuvette using a graduated plastic pipette. Later, we will label the cuvettes from 1 to 10, starting with the cuvette with the highest concentration of sunscreen. Finally, we will record the UV index of each solution using a UV meter. Now, something important to note, in order to reduce random error, we will need to repeat the recordings at least 3 times and take an average. We will also record the UV index of an empty cuvette as a blank sample. Now we will repeat these last 8 steps, but now using the chemical sunscreen. Following the procedure described above, we're able to calculate and see the raw and processed data for physical and chemical sunscreen. So on the left, we can see how the cuvettes are labeled with their corresponding concentration, followed by their UV index reading for each trial, as well as the average UV reading. Following the next column, we can see the percent transmittance, which is the UV average reading over the UV blank reading times 100. The absorbance was calculated by using the simple equation of 2 minus the log of the percent transmittance. With the tabulated data, we were able to model the Beer law model for physical and chemical sunscreen. So as we see on the slope of each model, we can see that the chemical sunscreen has a higher or steeper slope than the physical sunscreen. Assuming that the path length for each cuvette is constant, since we use the same volume, we are able to find the molar absorptivity coefficient for each sunscreen. And knowing that the slope of the chemical sunscreen model is steeper than the physical sunscreen, we can already tell that it has a higher molar absorptivity coefficient. So in conclusion, this experiment allowed us to find the molar absorptivity coefficient of physical and chemical sunscreen and see that chemical sunscreen has a slightly higher molar absorptivity coefficient. Some possible improvement for this experiment would be to use a UV meter with a greater accuracy, as well as finding a way to explicitly find how much light is reflected back into the air. These are my references and any questions.